This is the second lecture for Chapter 10, and we will start off with the kinetic molecular theory. So we can apply this to any type of matter in regards to state, solids, liquids, or gases. It's most interesting, I think, with the gases because of, again, some of the properties that gases have, that they're spaced apart so much. So they're very manipulable. I like saying that. Looking at this model, we can see how gases behave. So we'll go on to a couple of the things here. First, gases have large number of molecules, and they're always in constant, continuous, random motion. So just something to know that this works for pretty much everything, but the gas particles, because they're so far apart, they're just constantly moving around. Next is the volume. We like to pretend that they have no volume, because in a gas it's almost infinite if there's not much in there. There's a lot of space between the gas particles, so we try to make the assumption that regardless of volume, there's no volume there, so we just ignore it. Next, we like to pretend, and these all pretend, that there's no attractive or repulsive forces between the particles. They all just bounce off each other with elastic collisions. That's one of the key words I like to say, that all the collisions are completely elastic. There's no attractive or repulsive forces. Okay, moving on. Looking at this graph here, the main thing we're looking at is what is the speed of the particles. And we're not going to spend a whole lot of time here, but just to kind of mention this. First, notice that this curve is not a bell-shaped curve. It kind of angles out a little further over here on the right. This peak is the most probable position for the energy of a particle. So, okay, we got that. Or actually, I should say the speed. But again, because we have this push out here on the right, the average speed is a little further out than the actual peak. And this here is called the root mean square, which is the energy that the average particle possesses, which is slightly different than the average speed. So there's some math behind the scenes that demonstrates that it actually is a little further out. This doesn't really go anywhere, so just to mention it. Something to mention though is as we increase the temperature of a gas, going from, in this case, 0 degrees Celsius to 100 degrees Celsius, a greater proportion of the particles will have energy that is further out of the curve. So as we increase the energy, notice that, again, this is not a bell-shaped curve. So if we draw a line down here, more particles are on this side, the greater percentage of the most probable position. So if you just think of it, if I increase the temperature, more particles have more energy. I guess that would be the easiest way to demonstrate that. Okay. So effusion. There's two definitions that sound almost the same. There's effusion and diffusion. Effusion simply means the ability of a gas to go through a hole. Think of a pinhole in a balloon. So you can ask what type of gases would be more easily able to go through a pinhole of a balloon. You could say high temperature. If they're at high temperatures, they're bouncing around more. They're going to hit the pinhole more. You could also say that smaller gases, because they're smaller molecules, they'll fit through a hole more easily. So two things you can think about for that. And this is the example that we're seeing here. We have two gases that theoretically would have the same amount of gas within them, but notice after a period of time, the helium balloon is smaller, and the reason it's smaller is because the particles are smaller and they're going through any holes a lot more easily. Also, because the particles are smaller, they're traveling faster because smaller particles will travel faster than large particles, so they're hitting the pinholes more easily. Diffusion. Diffusion is just the ability of a gas to spread through the room. So the example I like to use of that is someone with some serious case of axe in your classroom. They walk in and they're sitting in the far corner. After about the end of the class period, everybody in the room can smell that axe because it diffused equally throughout the room. Now, of course, that would be if the person left, but if they're there, it's still, punging off that person continuously. But the idea is the gas will travel and equally fill a space. All right, so Graham's law of effusion. We've seen this one before. It looks pretty nasty. It's not really as bad as it looks. I think it goes into a little more detail in the next slide here. These are supposed to be absolute, or not absolute, excuse me, square root signs. And if it's pretty easy to put together, if we focus on this part of it over here and over here, notice that the 2's are on the opposite sides. We'll develop it. Is it over on this slide? Let's take a look. No, it's not over there. So if we notice that, for example, the square root of the molar mass of 1 over the square root of the molar mass of 2, notice that they flip over here. We'll develop this in greater detail in class. It is on this slide, but we'll talk more about it in class. So, deviations from ideal gas behavior. Looking at this one here, this portion that you see over here on the left-hand side is looking at a gas with the pressure fairly close to 1. So notice, for example, even when you're at 1, you're having some slight deviations. So we notice that as the pressure of a gas increases, you got some wacky stuff going on. So these are really incredible values that we can put onto a gas, and we see that there are some derivations initially which would appear to decrease the amount of moles, the number of moles, and then of course it appears to go up. So we know that this Pivner equation isn't perfect. And we can look at the same scenario here when we put one gas, I believe it happens to be nitrogen gas, that if we influence both temperature and pressure, that we have a lot of interesting things. And it's difficult to make the comparison of two things at the same time unless we hold, for example, pressure constant in this case. So notice which one of these three gases is most ideal, or ideal conditions. And it would actually be this one here, that if we hold pressure constant as an example, 600 atms, when the pressure, or excuse me, when the temperature is really, really high, it's at least closest to an ideal gas. So, okay, we'll figure out what that means here shortly. So here's these derivations, and the main things we have to look at, and we'll go ahead and just write it in here somewhere. PV equals nRT. The main things we're looking at here is what is affecting the volume of a gas and what's affecting the pressure of a gas. So what we want to say ultimately, as it'll be on one of these slides here in a second, is gases most behave ideal conditions when they're at very low pressure or very high temperature. Well, we'll come back to that. Very high temperature. So when the temperature is high, these collisions are more elastic when the temperature is high. When the pressure is low, the particles aren't near each other, so again, they have fewer interactions, and they're not going to have attraction as much. Whoop. So we have to try to make some adjustments on that, and what these adjustments are known as is the van der Waals equation. And I think we have that written up here, right here. So these are some examples of some corrections we can put in that equation, but then we can ask the question, why? Why are we adding this variable into the equation, or this variable? So let's look at the correction for this one here on the left first. If a gas is at whatever temperature conditions, there could be some attractive forces. And if there are attractive forces, what is that doing to the pressure of the gas? Well, the pressure should go down because, if the gases are attracted to each other, they're going to have less volume and there's going to be less pressure as a result. So this factor here on the left is going to correct for that. And again, these are all individual to whatever gas you happen to be talking about. We have this A variable and B variable. So that is going to bring the value back up to ideal conditions. So that is why it is an addition. Now for volume, if the gases have volume, and they actually do, it's very, very small, that means it's going to be taking up more space than it really should in comparison to an ideal gas. So this variable here on the left will knock it back down to what is an ideal gas conditions. And you can notice with these values here on the left-hand side, for these various gases, as the gases become larger, there's more attractive forces. So that's why the values actually become larger, is to further compensate for the attractive forces that these gases have and the larger volumes that they'll have. Okay? That is the last lecture for Chapter 10. Got it done in 2 lectures. Great.